Hi. So we've been talking about the Coriolis force, which is this, and we came across a little bit of a puzzle when we were discussing this in class. Um, we know that for someone in the northern hemisphere, um, if they uh, fire a bullet or something north, um, an observer on the surface of the Earth will see an apparent movement to the east. And if he would fire the bullet east locally, it would curve south uh, with respect to his perspective, and all the way around this would happen, and which we get directly from this equation if we recognize that the angular velocity goes through the rotation axis of the Earth as drawn there. And if you just take these various cross products, you'll see that a projectile in the northern hemisphere always curves to the right with respect to where you aimed it. Um, which is fine. That's what the equation says. But the question is, how can this be? Because we know that the Earth is rotating in this direction. So the rotation of the Earth is going in the same direction as this bending. So it's not a trivial result. I mean, this picture would be easier to understand if the Earth was rotating the other way, right? Um, because then, as you fired it north, the spot where you aimed it to moved to the left, and thus you missed to the right. But that's not the case. The Earth is rotating towards the east, yet the projectile still bends towards the east if I fired it north. So how can that be? It seems backwards, or it seems counterintuitive. It is exactly what is supposed to happen, and I sorry for not coming up with this mental picture when I was asked. And this is the first chance I've had to make this movie. So let me share with you the mental picture that you need to understand this confusing thing. Um, let's imagine the Earth again, and it's rotating, and that means, and it is rotating in this direction. It is rotating this way, and the spot that's behind the Earth, behind this picture that I can't see, is rotating that way. That is the sense of this. Indeed, what is happening. Um, but and we can also draw this from a top view. So this was a sort of isometric view, and this will make a top view. And now, so the rotation axis is coming right at me. The omega vector is coming right at me, right there. And imagine a place, say Miami. No, that's not what I wanted to pick up. Let's get rid of this. And another place, Detroit here, or I don't know, even farther north. Okay, so those 2 points would be here, and let's look at their tangential velocity. This guy is moving this way, and this guy is moving this way as the Earth is rotating. If we just look at where these points are, as the Earth rotates in a short time interval, this point will move to the right, and this point will also move to the right because the Earth is a rigid body. And let me move these points just to be a little clearer. I'll move them to this side and this side, which makes a little more sense. Okay, so now this point is moving to the right, and this point is moving to the right. as the Earth rotates. But obviously, in one day, this point is going to move around the circle, and it's going to come back to exactly where it was before, as is this point. It's going to go around the circle. It's going to come all the way around to there. So both of these points return to their same position after one day, after a period of one day. But obviously, these 2 points are moving through very different distances. This point, oh, that was the wrong pen. This point here is a distance from the rotation axis of say rho inner, and this point here is moving at a larger distance from the rotation axis rho outer. Right. So that Miami, or whatever I drew here, Mexico City, is farther away from the rotation axis of the Earth than points north are. Okay, so in one day, a place on the surface of the Earth moves through a circle of circumference 2 pi rho inner, and it does that. It does that with the angular velocity. It does that. So this is the tangential velocity, and then this is the period. So this is just distance equals rate times time, with the tangential velocity given by the angular velocity of the Earth times this distance from the rotation axis. This was just another way of writing that 2 pi is the angular velocity times the period. I just multiplied both sides by the distance from the axis. So you can see, and likewise, if I would be standing on the North Pole and looking down at the ground at a point one foot away from me on the ground, that point would go around a circle, and it would travel, I don't know, 5 feet, but it would 5 feet total as it goes around this circle, and it would do that 5 feet in one day, and then in Detroit, whatever it is, it may go some many thousands of miles in one day, and Mexico City will go even farther, twice that. I don't know what the exact number is, maybe 20%, 30% more miles per day, because they all end up returning to the same point they were one day later. So the tangential velocity of a point on the Earth close to the equator is large. The equator is got the highest tangential velocity that one can have. That point has to move the farthest distance, the full circumference of the Earth, in one day. But at any other surface, at any other point on the Earth, it doesn't have to move that far because of the shape of the Earth. The Earth is round. So, okay, so now let's draw this picture again. So if I'm somewhere and I've got a gun, and my gun I haven't fired it yet. It's just sitting on the ground. And I'll leave that gun sitting on the ground for days. And so this gun will just go around in a circle, around and around and around with a bullet in it. But it is moving at a large tangential velocity because it's close to the equator. All right, so before even firing the gun is moving to the right with a large velocity because it's close to the equator. And I fire the gun north. But I fired it at a point up at a higher latitude, where the tangential velocity is much smaller. So this was the velocity of the gun where I'm just drawing a vector here to make a picture to help you visualize this. But the gun itself, before firing it, is moving with a high speed to the east. The gun itself, the mechanism that's going to fire this bullet. Eventually I'll fire the bullet. This is the bullet. And it starts moving north, right? So I fire the bullet, it's going to start moving north. but the bullet has the same eastward velocity that the gun did. So everywhere that the bullet is coming, it's moving with this uh, uh, initial velocity of the gun itself. And so um, the net is that the net velocity has a large eastward component due to the tangential velocity of the Earth at that location where I fired the gun. And I fired it north, where the tangential velocity, here's the velocity of the target, that's the velocity on the surface of the Earth where the bullet is, where I've aimed the bullet. That is not moving eastward as fast as the gun was. So uh, I don't know exactly how to draw this picture, but the bullet is eastward of where the target had moved to, because the tangential velocity of the gun itself and the bullet before it was fired was at this location of the Earth is much larger than the tangential velocity of the target. And so the bullet carries that tangential velocity. It's not just moving north. I mean, I fired it north locally, and as far as I was concerned, as the guy shooting the bullet, it was moving north. But the gun and the bullet and me were moving at my location eastward with a high velocity, whereas the target north of me was moving eastward with a much smaller velocity. So indeed, the Earth is rotating eastward. Indeed it is. But the shape of the Earth is such that the target location north of me was rotating eastwards more slowly than where I fired it. And the bullet has the initial velocity, the initial eastward velocity of the Earth at the location where I fired it. So that's why if I fired it north, the bullet appears eastward of my target. And the same arguments go if I would be up at a high altitude, sorry, I keep saying altitude, a high latitude, and I fired a gun south. And now the tangential velocity here is very small. The bullet does not have a lot of eastward motion right out of the gun, because the tangential velocity at this location on the Earth is small. But my target is down here closer to the equator, and it's moving with a very fast tangential velocity because it has to go all the way around a much larger radius in one day than does this point up here at a higher latitude. And thus, you know, with respect to the target, the bullet ends up coming up short of making it all the way to where it would need to be directly due north, south, because the bullet's eastward velocity as it was fired is much smaller than the eastward velocity of the target, just because of the shape of the Earth. And so it's because of the shape of the Earth that we get, if we fire it due north, we get a component of that trajectory that is like that, which is parallel to the rotation axis, and this part of that will not cause any Coriolis force, and we have a component of the initial velocity which is in, and this component crossed with this component will produce the bending to the right. So this is entirely because of the shape of the Earth and the fact that the surface of the Earth is moving around the Earth at different radii, different velocities depending on its latitude. You think about this for a second. With the if say the Earth was a cylinder, just for fun. And there's the same rotation axis. And here I am somewhere on the side, and I'm going to fire my bullet north. All right, so this was the isometric view, and let's do a side view. So here I am at this someplace near the equator, and I'm going to fire my bullet north. In this case, we can simply use our equations, and the velocity is parallel to this. The velocity is parallel to the angular velocity vector in this case, right? So we know that v cross omega has to be 0 because they're parallel. There's no component of the velocity vector which is not parallel to the angular velocity. So v cross omega is 0, and there would be no Coriolis force in this case. But that's easy to see also from this picture here, because if it's a cylinder, then every point on the surface of the cylinder is moving to the east at the same speed everywhere on this side of this cylinder. This point here is moving at the same tangential velocity. All these points are moving at the same tangential velocity on the surface of the cylinder because it's a rigid body. All these velocities are the same. So that means that the velocity of the gun and the bullet before it's fired is the same as the velocity of the target. And thus there will be, as the bullet goes north, it will simply, and the target will simply track. Both the target and the gun are moving eastward at the same velocity, and I fired it due north. So in the end, everything's going to work out, and I'm going to nail my target. No problem. No problem. There's no Coriolis force in this case, as we knew. But we can also see that it's also because these tangential velocities on the surface of the cylinder, as I move quote-unquote northward on the cylinder, are all the same. So this is the right mental picture to use to understand why things, when fired in the northern hemisphere, curve to the right. An interesting exercise for you to do is to imagine what happens to projectiles if they're exactly at the equator. What happens if I fire something due east exactly at the equator? That the Coriolis force is actually up in that case. And if I fire due west, the Coriolis force is down locally. It's actually interesting. Right at the equator, the Coriolis force pushes up or down. But in the northern hemisphere, no matter what direction you fire with respect to the surface of the Earth, it curves to the right from the gunner's perspective, and that's because of you can either picture it just from the equation we derived, but another way to picture it is to think about how the tangential velocities of the surface of the Earth depend on the latitude or the polar angle. Same thing. All right. So hopefully this helped clarify these Coriolis forces. They are a little mind-bending sometimes, but it does make sense. And these images that we've been drawing, you can either make sense of it graphically, or you can just use the equations, whichever works for you. All right, hopefully this helped. If it didn't, let me know, and we'll try to figure it out together. Okay, take care.